Here is a number to sit with. 1 hour. Not a semester, not a certificate program. 1 hour in a hotel conference room, and a group of nurse anesthesia faculty walked out with their belief in using AI for real academic work nearly doubled. The average went from about 21.5 to almost 42, on a scale topping out at 50.
And it is not just that the average went up. The scores also pulled together. Before, people were all over the map. After, they clustered near the top. A bigger number and more agreement at once. That is what makes this project worth talking about.
So let us dig into it. A completed DNP scholarly project by Jason Duprat, a CRNA. He built a 1-hour hands-on AI workshop, ran it at a real conference, and measured whether it moved something called self-efficacy. What the project did, why the design choices were smart, and what the results honestly show. So why does faculty and AI matter enough to build a project around?
Because there is a workforce problem underneath it. Nurse anesthesia has a documented, decades-long faculty shortage, driven by workload and burnout. One task force report showed roughly 15% annual turnover among program administrators over 4 years. AI can genuinely cut the time spent on routine academic tasks, but you cannot adopt a tool you were never trained to use.
So the bottleneck is not the technology, it is the person's belief that they can work it.
Exactly, and that is where the theory comes in. Jason built the project on Bandura's self-efficacy work, and it has 2 layers. Layer 1, the why. Self-efficacy, your task-specific belief that you can do a thing, is one of the strongest predictors of whether you adopt a new skill. You cannot follow faculty for a year, but you can measure the belief that predicts the behavior. That is why he made it the outcome.
And layer 2?
Layer 2, the how. Bandura named 4 sources that raise self-efficacy, and Jason used them as a build checklist. Mastery, doing it yourself, the hands-on practice, vicarious experience, the live demonstrations, verbal persuasion, coaching, and your emotional state, which he addressed by naming the AI fears out loud to lower anxiety. The 4 sources were the design checklist. Self-efficacy predicting adoption is why it's the outcome.
So the theory designed the room. What did the hour actually look like?
Hands-on at the AANA Sand and Surf Symposium in Florida, using one free tool, Google NotebookLM. He taught 5 specific skills: write measurable course outcomes, map them to the COA graduate standards, map them to the AACN DNP essentials, generate cited multiple-choice questions from your own content, and review test items for flaws like ambiguity or 2 right answers. Each was a live demo, then attendees ran the prompts themselves.
And I noticed he measured 5 things. That is not an accident.
It is one of the strongest parts of the design. The 5 skills are word for word the 5 items on the survey. In research terms, that is construct alignment. He is not measuring some vague halo effect. He is measuring belief in the precise tasks he coached.
But why these 5?
He used the AANA Task Force's own needs assessment, which ranked 5 domains of need. The number 1 domain by a wide margin was academic, with 40 first-place votes. Course outcomes, test development, item writing. Number 2 was curriculum, the accreditation mapping. He taught straight from the top of the list, then kept only the tasks generative AI is actually good at.
All right, the moment of truth. What did the data show?
2 questions. How far did scores move, and how broadly? The composite runs 0 to 50. The median went from 24 to 41.5. The mean went from about 21.5 to about 42. That is the nearly doubled headline, a 94% jump.
And the tightening you mentioned at the top?
The standard deviation, which is just how spread out the scores are, dropped from about 17 to about 8. Before, wide scatter. After, everyone bunched near the top. Agreement, not noise. And every one of the 5 tasks rose by roughly 4 points on its 0 to 10 scale. Broad, not one lucky item carrying it.
So it sounds like a slam dunk, but you promised the honest version.
Here it is. The primary statistical test came back at p equals 0.057, and the line researchers care about is 0.05. So it missed the cutoff for statistical significance. By a hair, but it missed.
Explain the p-value like I am a normal person.
A p-value answers one question. If the workshop truly did nothing, how likely is a jump this big by random luck? Tradition says under 5% earns the label statistically significant. His answer came out to 5.7%, just over the line.
So the workshop did not fail. It is just too close to luck to plant a flag.
Right.
A result like this is inconclusive, not negative, and there is a reason to think the effect is real, even though the test missed. Statistical power. His analytic sample was 9 responses before and 8 after. That is tiny. When a study is that small, the test can only catch very large effects. A real effect can be sitting right there, and the study is too small to see it.
And that has a name.
When a study misses a real effect because it was underpowered, that is a type 2 error. But here's the careful part, worth copying. Jason says the result is consistent with a possible type 2 error. You can suspect one, you can never prove one, because you can never be certain the effect was truly there. So the language is always possible or consistent with. Never, it definitely was.
And one more phrasing rule.
Because the surveys were anonymous and unlinked, he cannot say the same people improved, only that the post-workshop respondents scored higher than the pre-workshop respondents. 2 piles of answer sheets, not matched pairs.
Which is exactly the kind of thing a sharp reader circles in the margin. So let us do 3 of those questions and the project's answers. First,
Number 1, the unlinked surveys. How do you know the same people improved? The project does not claim they did. No one's before answers can be matched to their after answers, so the comparison is 2 groups, not 1 over time. Anonymity was the IRB-approved design that protected participants. The cost was tracking individuals. Linking each person's before and after is the obvious next step for a replication.
Question 2 is a stats trap. One participant scored a perfect 50 before the workshop even started. Did the project test with that outlier bid?
In a group of 9, one extreme value drags everything around, and the handling is strong. He ran a sensitivity analysis, rerunning the numbers with that person removed to see if the answer flips. It does. Take that person out, and the primary result becomes statistically significant, but he kept them in.
Wait, he kept the data point that hurt his result?
On purpose. Removing data to get a prettier answer is bad practice. The p equals 0.057 he reports is the harder, more honest version, and he reported it because it is correct.
Question 3. He ran other tests on the side.
He checked whether age or gender was related to the scores. For gender, a Mann-Whitney test. Not significant. U equals 4, P equals 0.39. For age, a Spearman correlation. Also not significant. Rho about negative 0.2, P equals 0.31. So the gain was not just some subgroup. But watch the landmine. There are 2 different Mann-Whitney results. That gender test, U equals 4, and a supportive one, U equals 10.5, P equals 0.015, comparing pre and post scores, which did cross the line.
So why not lead with the significant one?
Because that was not the pre-specified primary test. You do not switch your headline test after you see which result looks nicer. The significant one is supportive evidence, and it stays in a supporting role. That is integrity, and it is what peer review rewards.
So pull it all the way back. What is this project really about?
Nurse anesthesia education has a workload problem, pushing people out. AI is a credible part of the solution, but only if faculty believe they are capable of using it. That belief is self-efficacy, and it predicts adoption. After a single structured hands-on hour, the post-workshop respondents reported far higher and far more uniform self-efficacy across every task taught. Underpowered, not unpromising. The right next step is an adequately powered replication.
And here is the line that stuck with me. We spend so much energy asking whether students are ready for AI. This project flips it toward preparing the educators.
You cannot ask faculty to guide students through a tool they do not feel capable of using. Start with the teachers.
Before we close, a word to the doctoral students listening. This project models a few things worth stealing for your own scholarly work.
Pre-specify your primary test and stick with it, even when another result looks shinier. Keep the inconvenient outlier in and report the harder number. When a small sample lets you down, frame it honestly, consistent with a possible type 2 error. Align your theory to your measure so every item traces back to something you taught. And notice a rigorous pilot can be small and feasible.
So the takeaway is not go big.
It is go careful. A tight question, a theory that does real work, honest statistics, and a clear next study beats an overreaching claim every time. That is what good science sounds like.
Prepare the educators, not just the students, and design it so honestly that the limits are part of the finding. That is the one to remember.